All right, we are moving now into chapter 3. And actually, once you do some work on chapter 3 on determinants, the second MATLAB assignment is going to make more sense to you, and we're going to then have an opportunity to discuss it, and it'll make more sense. But MATLAB determinants, section 3.1 is determinants. So let me just bring up a quick example here in Blackboard. Okay, so a 2x2 matrix, 1, 3, -5, and 4. So if we want to find, if this is our matrix A, and we want to find the determinant of matrix A, there's several ways to denote determinant. Okay, so DET is used a lot in the book for determinant. That's certainly one way to denote it. Let's see. I'm trying to think if they have any other. That's sort of the notation that they use. But actually, the determinant of A, symbolically, what they do is use this symbol, the absolute value signs, like this. So, but this means determinant. It doesn't mean you're not taking the absolute value of a matrix. When you put those absolute value signs around the entries of a matrix, it means determinant. Now, for a 2x2, it's pretty simple what a determinant is, right? How it's defined. How would it be defined? How would we find the determinant of this 2x2 matrix? Do you remember? 1 times something minus, good, that's right, Jonathan. A times D times minus B times C. So that would be 1 times 4 minus -5 times 3. And so that's going to get you 4 plus 15, which is 19. And that's your determinant. So the determinant of a matrix is, with entries, is a scalar. It's a number. And a lot of courses, well, you've probably seen this in some of your courses, the determinant of a 2x2 matrix. And how many have seen that before in their travels? Well, Jonathan, that's right. When you're finding the inverse of a 2x2 matrix, the determinant is used. That's right. Now, you could also say, maybe like, let's say we had another matrix A that had entries 1, 3, 0, -5, 4, 2, and 1, 3, 6. 3x3, 3x3, okay? And you want the determinant of that matrix. So I don't know if you've seen this before, but in teaching calculus 3, multivariable calculus, I know that for a 3x3, there's a little trick in computing the determinant of a 3x3 matrix where they write the first 2 columns down like this, and then what they do here, and maybe let me change the font size of my pen here. Hold on. Yeah, that'll do. Well, that's a little bit too thin. Hold on. I don't know if you've seen this. You multiply those three numbers, you multiply those three numbers, you multiply those three numbers, add them, and then, so it's three products that you compute and add, and then you subtract this product, and this product. Okay, so Mikhail says that looks familiar. How many have maybe seen that in a course where they had to compute a 3x3 determinant? How many of you does that ring a bell? Ring a bell? Okay, Jacob recalls that. Okay, and so yeah, that sounds good to me. So these techniques are fine for the 2x2 determinants and 3x3 determinants. But what if we had a 4x4 determinant or a 5x5 determinant? Okay, what if we had something like that? We need a more general way to compute a determinant. And there is a definition of the determinant whose results would give you the same results for a determinant of a 2x2 and a 3x3. You get the same results. And hold on here. The approach we're going to use, okay, hold on, let me just find it. One moment. Yeah, let me go down here a little bit. So they talk about how the determinant's defined, but this is the definition, the linear algebra definition of a determinant. And this approach is, well, it's called cofactor expansion. And this approach, you're doing cofactor expansion along the first row of the matrix. And just looking at it, it's a little kind of hard to, just look at it and, okay, there's the definition. We really have to apply the definition. We have to apply it. Okay, so let's do an example where we compute a determinant. I have one in the notes here, so let me bring it up. Okay, and let me give you a moment to copy this example down. Okay, so we're going to use an approach called cofactor expansion. Now, cofactor expansion can be utilized for finding the determinant of any square matrix. Determinants are defined for square matrices, n by n matrices. So what we're going to do is we're going to do this cofactor expansion, and we're actually going to you're going to see how that definition in section 3.1 is used. So we're going to use the first row. Now, cofactor expansion can be done along any row or any column, but let's expand. Let's expand along the first row. Okay. So that means we're going to expand along the first row. And let me show you how this works. Okay, so cofactor expansion along the first row. Let me give you a chance to copy down to here, and then I'll go into a little detail. Okay, so let me put the pen back to a little bit lower font. 3 is good. Okay, so let's look at this first number 1 here. So remember, the entries of a matrix are denoted by A sub ij. So what would the number 1, what entry would that be? This would be A sub, what would the indexes be? That's right, Mikhail, 1, 1. Because the 1 is in the first row and the first column of the matrix. Okay, so what we do is we put the 1 there, but we're going to multiply by the 1 by -1 to the 1 plus 1 power, because those are your indices, 1 and 1. And then we multiply that by the determinant of a submatrix, 4, -1, -2, 0. Now, how do we get that? What we do is we isolate out the first row and the first column. After all, -1 is in the first row and the first column. And the square matrix here is that submatrix. And we're going to find the determinant of that submatrix. And all of this together, this entire, let me just see here, hold on. Well, this portion, okay, this portion here is called a cofactor. It is called a cofactor, and we denote it by C11. That is a cofactor. We're doing cofactor expansion. Now, there are going to be three cofactors. Are there any questions so far? Okay. Well, then let me erase this and get to the next cofactor. Where did the negative? It's by definition that the -1 being raised to the appropriate power. It's just by definition, Mikhail. It's by definition, and it will work. Yeah. Okay. Let's look now at the 5. The 5 is in the first row, second column. Jonathan, it would make more sense to use the bottom row. Jonathan's saying, why don't we expand along the bottom row, because there's zeros in the bottom row, and it'll make our life easier. Yes, you could. It would make the best sense, or the third column. But since you're just learning here, I'm just going along the first row. The book, when it talks about cofactor expansion initially, it expands along the first row, just because, you know, it's convenient. The first row is like, you know, hey, it's the first row, you know. So, okay, now here's the 5. That's a sub 1, 2. And you're multiplying that 5 by, again, -1 to a power. Oh, what is the power? Well, because we have the 5 is in the first row, second column, we raise it to the 1 plus 2 power. And what we do here, hold on here, is we block off the first row and the second column. You could think of it like you know, like I'm showing you here. And the submatrix that results has entries 2, -1, 0, and 0, and that's the 2x2 matrix we use then. And so now this is the second cofactor. The -1 to the third power times the determinant of that submatrix. Okay, let's see here if there are any questions. Okay. Okay, we're good so far? They will, Mikhail, they will. These operations, this is a small matrix we're finding the determinant of, but a large matrix, it would be, well, we'll talk about that. We'll talk about that in just a moment. All right. Now let's go to the third entry in the first row. That's the 0. That's a sub 3, no, a sub 1, 3. And we block out, since that entry is in the first row, third column, we block out the first row, third column. And then this is the 2x2 matrix that results. And that's what goes here. And notice you have, you know, the A13 times the -1 to the 1 plus third power. And now you have your third cofactor. See that? So again, this is the we're really following the definition of the determinant on page 167 in your textbook. Okay, and it turns out the determinant is -2. It turns out the determinant is -2. Well, computer, yeah, we'll get to that. We'll get to that. So, are there any questions so far? All right. Well, let me show you something here. Let me go to the ebook. One moment. So this related to example 1. This was example 1 in section 3.1. But again, we can do cofactor expansion along any row or column we choose. And theorem 1 in the book mentions that. The determinant of a square matrix can be computed by cofactor expansion down any row or any column. And in terms of those -1 to the powers, okay, the -1 to the I to the power I plus j. Well, if you didn't want to kind of worry about that, I mean, you have to worry about it, but they have here just I mean, you know, either that portion of the cofactor is going to be positive or negative, and based on the entries, that little matrix there with the pluses and minuses in it tells you which entries are going to have a plus and which are going to have a negative. Like a +1, like the cofactors will either be multiplied by a positive. I want to be careful. That -1 to the I plus j power is part of the cofactor, but the portion, the -1 to the I plus j part, rather than write -1 to the 1 plus 1 power, -1 to the 1 plus 2 power, and so forth, all you have to do is just remember this little plus or minus matrix here. Like the top, the entry at the top left is in the first row, first column. So that's going to have a plus for the -1 to the 1 plus 1 power. If you move down, you would be in the second row, first column. So -1 to the 2 plus first power is -1 to the third. That's -1, and that's a negative. So it's just a nice way to remember the negatives and positives, that little chart there. It's actually quite nice. So let's look at that example again. And why don't we do cofactor expansion down the second column? So I'm not picking the easiest columns to do cofactor expansion on. That's for sure. It's just so though we get a little practice. So here we are again, cofactor expansion. So now we're going to do cofactor expansion down the second column. Down the second column. And I work it out for you here, but I can just sort of go through a few details here. No problem. So the first entry in the second column is the 5. And if we block out, the 5 is in the first row, second column. So if we, in our minds, remove the first row, second column, what's going to be left is 2, 0, -1, 0. And that's what you have here. Okay, and if we were then to go to the 4, and notice, I'll say, notice the entry is negative, right? So that little helpful picture where we had plus, minus, minus, plus, 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 minus, plus, it alternates. Doesn't even take any thought at all that, we have a -1 here in front of that determinant there. Are there any questions? Okay, well, let's do another one here. Continuing down the second column. Here's the 4. The 4 is in the second row, second column. So the submatrix that results is 1, 0, 0, 0. Okay, and then this -1 to the 2 + 2 power, that's a plus, as it should be. Because based on the little chart or the little matrix thing they give us, there it is. That's a plus. See how that works? Are there any questions? Okay. Well, let me go down. Let me find the. Whoops, hold on. Here is the third entry in that column. So that entry is in the second column, last row. Mikhail, the pluses and minuses just match. In front of every as part of every cofactor, you have -1 to the I plus j power. But you don't have to memorize that, because you have the little helpful chart. So now, like this number 2, we blocked out the first second column, last row. What we have is 1, 0, 2, 1. There it is, 1, 0, 2, 1. And we should get a determinant of -2, by the way. You can't get any cofactor expansion should give you the same determinant, and this is no different. This is no different. We get a -2. Now, a couple students noted that for cofactor expansion, okay, it would be easiest to expand along either the third row, because you have 2 zeros in that third row, So the cofactor expansion involves the sum of 3 terms. 2 of them are going to be 0 if you expand along the last row. Is there any column that might be good to expand along? We expanded along the second column. Yeah, that's right, Bellen. Use the third column. Use the third column. And in the homework, chapter 3 is not on your second exam, okay? But like in your homework for section 3.1, and incidentally, that homework it's not going to be due until this coming Monday. I want to give you time to study and prepare for the exam, right? And the window of time you have until, what is it, this Saturday, February 26th at 6:30 p.m. So, I want you to be concentrating on study. All right. What'll happen though in the homework for section 3.1 is they'll give you sometimes big matrices. They'll give you matrices of, could be like 4x4s or 5x5s or even 6x6s. And you have to think before you do the cofactor expansion which row or column would be the easiest to do. Okay, so let me just see here. I'm trying to think of an example. Let's say you had something like this. Let me think of another example here. Let's say, hold on, I want let's say you had a 4x4 matrix. Okay. Now, do you think this? Do you think the determinant for this is going to be? I mean, do you think the 1,000 here is going to? It's a big number. Do you think it could make the determinant complicated? This is a 4x4 matrix. And we're going to do cofactor expansion. So what column or row do you want to, let's think of a column. Well, and hold that thought. Hold that thought, Mikhail. Let me just put the, one moment here. I just want to put the 3 and 4 a little bit more to the right. Okay. Which column is the best column to expand along? Good, the first column. That's right, Mikhail. That's right, Balin. So if we expanded along the first column, okay, we would, there's the 1. We would, hold on. Let's just get one moment here. I want my zeros to be a little bit more, just a little more in line. I want it to be a little neater. That's really important in math, to be neat. And we want our numbers to be lined up. Okay. So, all right, we'll expand down the first column. And so we're going to block out the 1 is in the first row, first column. And we're going to have a plus 1 times this determinant. 2, 1 with 2, 1, 4. Oh, come on, man. Oh, this crazy pen. Hold on. Hold on, this crazy pen. One moment. There's a feature on it that I'll have to learn how to turn off. You know, like, oh, somebody's helping me out. Who can help me out? All right. Okay, one moment there. So there we go. There we go. And this 2 here, I might make it a little more, let me go to 5-point font to match. Thank you, helper. Whoever did that, appreciate it. And let me just line things up. Okay, Mikhail, I appreciate it. Just lining things up a little bit, but you're right. Okay. One moment here. So now we got this new determinant of a 3x3. What column do you want to expand down? This crazy pen. I don't know what's going on with it. Hold on, there's something stuck or something. Let me get, I don't know what's happening here. Hold on. Let me see, one moment here, class. Hold on. Keep it in your notes, keep it in your notes. I'm gonna take a photo of this. I'm gonna, this, come on. Okay, let me do this. I'm not gonna have messy notes. I'm not gonna do that. So let's do this again. All right, I'm gonna stick to 5-point font. Let's just proceed here. So we have, right, 1, 5, 0, and 3. 0, 2, 1, and 4. 0, 0, 2, and that scary 1,000 number. And then 0, 0, 0, -4. What we did was we said, okay, to find the determinant, we should expand down the first column. So we block out the first column and the first row, and we get a positive 1 times this submatrix. Now, what column should we expand along for the 3x3 determinant? What column? First column, I agree, Bellin. So here we go again. I'll circle the 2, and 2 is in the first row, first column, so I'll block off the first row, first column. So now what we have is this plus 1 times plus 2 times the determinant of the submatrix that results. So far, so good? Okay, can we do the determinant of this 2 by 2? What row or column, what column would we expand down for that 2 by 2 matrix if we wanted to do cofactor expansion? That's right, Belen. The first column. So I'll circle the 2. Hold on here, let's make things nice. We'll circle the 2. And we'll block off the first row, first column, first row. So what we have is we have the plus 1 times the plus 2 times the plus 2 again times then the determinant of -4. And the determinant of -4 is just -4. Okay, it's just itself. So you get 1 times 2. I mean, really what happens is you don't even put you just do this. So you have 1 times 2 times 2 times -4. That gives you -16. So do you notice, well, right, well, what kind of matrix is this? What form is this 4 by 4 matrix in? It's a square matrix for sure, Jonathan, but it's in echelon form. That's right, Mikhail. It's an echelon form. Or upper right, well, it's upper triangular because the non-zero entries are all above the diagonal. And you see, it turns out that when you have the determinant of a triangular matrix like this, the determinant is just the product of those diagonal entries. I mean, that's what we have, the product of the diagonal entries. See that? How many think that's pretty cool? Yeah, it is. And so in your homework, some of the bigger matrices, you want to kind of look for things like that. And that's right, Jonathan, it saves a lot of time. It saves a lot of time. Okay, and so, you know, let's say that you used cofactor expansion. Let's say that you use cofactor expansion on a 25 by 25 matrix. Okay, let's say that we had a computer that performed 1 trillion multiplications per second. Okay, how long to, let me just say here, hold on. How long, let's assume this 25 by 25 matrix also doesn't have like a lot of zeros in it. Let's assume it's a dense, we call it a dense matrix when there's not a lot of zero entries. How long to compute? So we have a, hold on here, a 25 by 25, the dimensions are 25 by 25 for matrix, this matrix A. How long do you think it would take to compute the determinant of the matrix A? And we're assuming that the computer performs 1 trillion multiplications per second. Okay. How long do you think it would take to compute the determinant of that 25 by 25 matrix? Take a guess. 0.1 second, Cameron. Okay. Okay, Jacob says, now I'm talking about doing cofactor expansion like you learned it in section 3.1. It's going to take longer than 0.1 second. Well, what I want to say is if the computer programming to do a determinant use cofactor expansion, it would take longer than a tenth of a second. All right, how long, Mikhail? Jonathan says it's even less time. I'm going to give you the answer here in a moment. Well, okay, and I'll tell you what. You know how long it would take? So Mikhail's thinking a long time. It would take 500,000 years. That's how long it would take. And I'll show you this. This is in the book. Let me find it here. Okay, and I don't know how much that, well, yeah, so take a look here at the numerical note. Now this book's maybe 5 years old. Okay, this edition. By today's standards, 25 by 25 matrix is small, yet it would be impossible to calculate a 25 by 25 determinant by cofactor expansion. Okay, and here, hold on. If a computer performs 1 trillion multiplications per second, it would have to run for more than 500,000 years to compute a 25 by 25 determinant by this method. How many think that's like, I mean, absolutely amazing? So fortunately, there are faster methods, as we'll soon discover. Okay, yeah. Okay, so what we have to do is, if we can find, okay, Mikhail is, okay, saying about 500,000 years using, so very nice. So, yeah, Jacob, that's amazing, right? So, you know, computers are nice, they do computations, but even they have limitations. And that's why we need the mathematics. We have to find a way to compute a determinant quickly, because in real life, there are large determinants that have to be computed. And this will lead us into section 3.2, which is properties of determinants. Okay, and we will get into section 3.2 next. But are there any questions here? Okay, let me stop the recording then. Excellent.